Welcome to the final video in a series of 4 on the unit circle. Here we'll use the sum, difference, double angle, and half angle formulas. Before we get into the content of this video, it's imperative that you have a good understanding of problems from video 3. So you're going to either want to go back and watch that video if it's been a while, or at least pause the video here as I show you some of the problems from 3 and look them over, and you'll know if you're ready to move on to video 4. First, we did this problem in video 3. You may want to hit pause and study this carefully. Again, a more thorough explanation can actually be seen in video 3. We're going to make reference to this problem. Hit pause if you need to study the details here. And finally, this problem here will also be mentioned in this video, so either watch video 3 or hit pause and study the details here. So we'll make reference to those problems later in the video that you just took a look at. But for now, remember the concept here in these trigonometric problems is that you're given some information and then you're asked for some other information. Now, this is not the kind of problem that is the topic of this video, but it sets the stage nicely. Watch this. Suppose we were to want to know the cosine of a minus b. And let's say we were given the value of a and given the value of b. Well, I would just plug in the values of a and b, and I would work this out, and that would be the end of it. Now, as working it out, it's worth noting that functions do not distribute. What you see maybe in red here as your bottom line, that's not correct mathematics. Now, there are functions that do distribute, but they're rare, and cosine is definitely not one of them. In fact, none of the trigonometric functions distribute in the way that you see on your screen. So that bottom line is wrong, and be careful never to do that. Well, if that's not what you do, then how are we going to do this? Well, let's think back to the order of operations from basic algebra. The order of operations states many things, one of which is that you have to work out the arguments of functions first, or you could think of it as what's in the parentheses first. So I can't apply the cosine until I simplify what's in the parentheses. So pi minus pi over 3 turns out to be 2 pi over 3. For some people that's obvious. If it's not, hit pause and check out my arithmetic here. Okay, now I'm using the order of operations. I've worked out the argument of this function, and now I can apply the cosine of 2 pi over 3. By the way, in case you forgot, 2 pi over 3 was one of our main 16 points on the unit circle. So I won't show the work here. It's quite extensive, but presumably you've mastered the unit circle if you've gotten this far, or at least gotten close to it. And so this thing would eventually work out to be -half. Again, the work isn't shown here. But what I wanted you to see in this problem is not to remind you of the points on the unit circle specifically, just that if we were given a and b, we could plug them in and solve this problem. We wouldn't need to deduce information like we did in video 3. There's nothing to deduce here. They told us what a and b are, we plugged them in, we got an answer. End of story. But what if, instead of being told the value of a or told the value of b, I were just given information about the trigonometric values at a and b? And this would pose a slightly different situation. What I could do here is, given the information about angle A, I could deduce as much as I can about the terminal point of A and see how far that gets me. Now, You'll recall in video 3 that when presented with this information, you may see it in red in the upper left corner, we did some algebra by plugging 3/5 in for the y coordinate, and eventually, through a long process, we determined that A is an arc that terminates right here. And that point turned out to be -4/5, 3/5. So now I've deduced the terminal point of A. I don't know what A is, but I know where it ends. We could now do the same logic as we did in video 3 to determine the terminal point of angle B. You may recall in video 3 that we plugged in -5/6 for the x coordinate into the unit circle equation, solved for y, and through a process of deductive reasoning, concluded that B has to terminate here. And that point we also found. Now, I'm only a couple minutes into this problem, but if you were solving this yourself, it would take you a long time to get that far. I haven't even addressed the question yet. The question is to find the cosine of A minus B. But for now, notice, I was given information about A, I found the terminal point of A. I was given information about B, I found the terminal point of B. Why is that helpful? Well, you're about to find out. So let's look at our question. We want to find the cosine of A minus B. Now remember, functions don't distribute. So if I were to try to find the cosine of A minus B, I would have to know what A minus B worked out to, or so it would seem. But remember, we don't know the value of A, and we don't know the value of B. And even if we could find values, or I should say angles that terminate at those same points, remember there are infinitely many angles that terminate at any one given point. So I really don't have any way of accessing the value of A itself, nor the value of B. Well, that seems like we're at a standstill then, because we can't compute this quantity without doing what's inside the parentheses first, and we don't know what's inside the parentheses, therefore it seems that we're stuck. Which would be true if it weren't for this amazing discovery centuries ago. Mathematicians were able to prove that the expression on the left, the question, and the expression on the right, which looks nothing like it, always have the same value, no matter what A and B are. And if they always have the same value for any A and B, then they're going to have the same value for our specific values of A and B. By the way, just as a vocabulary note, when two expressions always have the same value, regardless of the variables themselves, we call that an identity. But regardless of what we call it, we're going to exploit this discovery. Here's the logic. This is what we want to compute. What if I could compute this instead? By computing the thing on the right, whatever answer I get will be the same as the expression on the left, or the question I'm trying to answer. Now, why would I want to take the problem and make it more complicated? Well, because for the expression on the left, which is the question being posed, I need to know the values of A and B to do that, and I don't know them. But for the expression on the right, and here's the amazing part, I don't need to know the values of A and B to compute trigonometric functions at A and B. I only need to know where they terminate, and that I do know. So I'm going to compute the expression on the right, and whatever answer I get, I will know by the mathematical identity discovered centuries ago that has the same value as the question I'm trying to answer. So now let's go about computing the expression on the right, factor by factor. Let's start with the cosine of A. The cosine of A, by definition, is the x-coordinate of the terminal point of A. But we know where A terminates, right? And there's my x-coordinate of that terminal point. So that's the value of the cosine of A. The cosine of B is by definition the x-coordinate of the terminal point of B. Well, here's the x-coordinate of the terminal point of B, so I can substitute that in. And so the process goes. Next, the sine of A is the y-coordinate of the terminal point of A. But look at the top of the screen. I already know the y-coordinate of the terminal point of A. Plus the sine of A was the original given information anyways. And finally, the sine of B is the y-coordinate of the terminal point of B. That's right here. And I can plug that in as well. All I have to do now is simplify this expression. And not only will I have the value of the expression on the right, but of course I will also have the answer to my question on the left. By the way, I did this on scratch paper, and here's the answer I got. It takes pretty simple algebra to see how I got this. I simply multiplied these fractions and got positive 20/30. That reduced to 2/3. And I multiplied these fractions, and I got positive 3 radical 11 over 30, which reduces to radical 11 over 10. And so you can see, there's the answer, by the way. So you can see here that we found the value of the cosine of A minus B without ever finding the value of A or B themselves, just by using this identity that was discovered. So we just saw how we could use a mathematical discovery known as a trigonometric identity to solve a problem that we couldn't otherwise have solved. Now it turns out there are hundreds of mathematical identities, especially in trigonometry. And the purpose of this video is not to give you an example of how each one could be used, because they're all used basically the same way. Generally, we're not expected to memorize them, but just to prove a point, I looked up a few of them on the internet, and I found these 4 identities, or 8 really if you consider the plus or minus option in each one of them. And here, for example, is the one we used on the previous problem. These are generally called the sum and difference identities because they give you the sine or cosine or tangent of a sum or difference. I also found these identities on the internet. They're called the double angle formulas because each one of them gives a trigonometric function value of 2 times an angle, or 2a in this case. I also found the half angle identities as well, and there are many, many more. These identities that you see in front of you here are typically the ones that are used in a trigonometry class. And again, the purpose of this video is not to show several examples of how a variety of these formulas can be used, but it's just to show you that there are tons and tons of trigonometric identities out there. Here are the main ones, and you can use them all to answer questions as they arise. And that completes the 4th video and this series on the unit circle. Thanks for watching.